Okay, so we're going to continue on with section 7.1, integration by parts. This is part 3. So the formula we've been dealing with is, so the integral u dv by integration by parts is going to be uv minus the integral v du. And so what we've seen is, we can use this formula. So there've been a couple of different types of problems where we've used this, and if you need to, if you have something that you can differentiate a bunch of times and get rid of, like an x to the x or an x squared, it works really well for that. I'm going to show an example that's pretty important because so a lot of people don't know how to do this integral, and it's an important one to know how to do because it pops up in a couple places. So let's evaluate the integral e to the x sine of x dx. So when we're doing this integral, so you'll notice that can't think of an antiderivative just right off the top of our heads. It's not u substitution. I don't see the derivative of e to the x or sine of x anywhere. So it looks like we're gonna have to use integration by parts here. So we need to pick our u and our dv. And for u and dv, you can pick it. So actually, let me take a step back. We'll get there in a second. So first thing I'm going to do is I'm in anticipation of what's going to happen. I'm going to call this integral I. I'm going to say this integral is equal to the letter I. So let's go through and do this. So we have the integral e to the x sine of x dx. I'm going to try integration by parts. I'm going to pick my u and my dv. I'm going to do it off to the side a little further. So u dv. So you can pick whatever you want. The first time around, you're going to have to do this more than once, but whatever you do, just stay consistent with it. I think it's easier to differentiate the trig function and integrate e to the x, but it's personal preference. So du then is cosine of x dx. V is e to the x. So when I apply integration by parts, I'm going to get uv, so e to the x sine of x minus the integral v du. So I'm going to get e to the x cosine of x dx. And okay, so I have this first term here without an integral, but now I need to integrate the second term. And it's just like what we had to begin with almost. I can't do u substitution. It's not something I can think of an antiderivative of off the top of my head. So we're going to try integration by parts again. See what happens. So we're going to do the same idea. I'm going to let u be the trig function. I don't want to do it the other way around because then I'm just going to undo what I've done. So u is going to be the trig function cosine of x. V is going to be e to the x dx. Du will then be negative sine of x dx, just taking derivative, multiplying by dx. V will be e to the x. So integrate dv. And now I'm going to get this is equal to e to the x sine of x minus, and then this integral is going to be uv, so e to the x cosine of x minus the integral v du, e to the x minus sine in front, sine of x dx. Let me separate that again. We're going to keep going, see what happens. We're going to simplify this. So this is equal to e to the x minus e to the x sine of x minus e to the x cosine of x. And if I, cancel out those, so let me double check to make sure I have all the minus signs right. So 2 minus signs here, plus a third minus sign. So I'm going to have a minus sign overall. That's good. Minus the integral e to the x sine of x. Okay, so I've simplified it, and this is what I'm left with. So what I'm going to do now is I'm going to go back, and what I've started with was the integral e to the x sine of x dx. I applied integration by parts 2 times, and I found that this is e to the x sine of x minus e to the x cosine of x minus the integral e to the x sine of x dx. And I dropped the dx up here. So what you'll want to notice now is I called this integral up here I before. The reason I'm going to do that is I'm going to write I is equal to e to the x sine of x minus e to the x cosine of x minus, if you look at this integral here, e to the x sine of x dx, well, that's the exact same integral that I have over here, e to the x sine of x dx. So I can call that I. And now this is an equation to just solve for I. So if I add I to both sides, I get 2I is equal to e to the x sine of x minus e to the x cosine of x. So I is then equal to e to the x sine of x minus e to the x cosine of x divided by 2. And then, yeah, so don't forget your integration constant here. So we can add it, we'll add it there. The reason being, you know, if I replace I is the integral e to the x sine of x dx. This then is equal to e to the x sine of x minus e to the x cosine of x divided by 2 plus my integration constant. And that is the solution to that problem. And you'll see, you know, this is another area, this is another time when integration by parts is really useful. It's when, so it's formula, it's integrals of this type, e to the x sine of x or e to the x cosine of x is a good one. So things like that where, you know, if you integrate or differentiate so many times, you end up with the same integral that we saw here. So we had the same integral here, and it gave us an equation to solve for that integral. So I'm going to stop here for this video because that was a long example. I'll pick back up with, it looks like, a couple more examples before I stop.